Till now, we have discussed the band theory of solids in terms of Bloch theorem and Kronig-Penney model. Actually, we have seen how the Kronig-Penney model to the potential describes the behavior of electrons in crystal in a quite simple way, and it leads the formation of certain allowed energy bands separated from the forbidden energy bands. Okay. In fact, you have seen that in this Kronig-Penney model, we have considered a very simplified version of potential, which is actually called a square wave potential of this type, which I am showing in this figure. But you know, this potential is not realistic. This is completely a hypothetical, or you can say an ideal potential. The actual potential that exists inside the crystal lattice or inside the crystal surface, you have seen in the introductory lecture of band theory. And actually, those potentials have this periodic variation, and at the surface this symmetry was deviated. But we have considered a very simplified version of potential which does not exist actually. Okay. So the KP model describes the behavior of electron moving inside the crystal in an ideal situation. So definitely the result obtained will be not very accurate. Okay. In fact, we have seen that when we discuss the KP band theory on the basis of KP model, then we get the allowed energy bands separated by the forbidden energy bands or forbidden energy gap. Okay. In fact, the significance of this form of the relation in the dynamics of electron in an electric field is described in terms of the a quantity H cross K, which is actually the momentum of the electron moving in this periodic potential with wave vector K. But this momentum of electron is popularly called crystal momentum. Okay. And in this case, the behavior of electron is quite similar to that of the free electron, except that an appropriate effective mass M star has to be substituted for the free electron mass M, and a nearly filled band has to be treated as containing the positive charge carriers, that is holes. Okay. So these were the basic facts regarding this KP model. What I want to tell you is that in this model we simply treat the electron like a free electron, but electron is actually moving in a periodic potential, but our aim is to treat it like a free electron. Then what is done? Actually, if a bonded electron or an electron moving in a periodic potential can be treated like a free electron if you simply replace the free electron mass M by the effective mass M star. Okay. And if the band is nearly filled, not completely filled, then another charge carrier also exists in those bands, and that is called positively charged holes. Okay. So actually this model, which we have discussed earlier in very detail, is actually highly artificial and is poorly related to the precise form of potential. Okay. Like this, which actually exists inside the crystal. And so consequently, these qualitative conclusions are only illustrative. Okay. An exact description of electronic behavior in a crystal must take into account the actual potential experienced by the electron due to the ion cores and all other electrons of the crystal. Okay. So actually this is a very complicated problem, and due to the complexity of this problem, such problems are handled or solved by two important approximate method. As you have learnt in your course on quantum mechanics, the approximate methods, but the perturbation theory. Okay. So actually that perturbation theory which you have studied definitely in your course on quantum mechanics, that is applied here to deal with the problem, because when we will actually consider the actual state of affairs, the problem will become very complex, because here there are two sources of potential. One is the ion cores and another is the other electrons. It means if you are considering the motion of an ith electron, then all the remaining electrons also contribute to the potential. So the actual behavior of potential under which the electron is moving, that potential is created by two sources, ion cores and the other electrons. So the nature of that potential is very complicated. So if we will write the wave functions of electron taking the actual potential under account, that will be a complicated case. Okay. So to solve such problems, two approximate methods have been devised, and those two approximate methods are called, first one is called Nearly Free Electron Approximation, NFE, and the another method is called Tight Binding Approximation, that is TB approximation. Okay. When you actually our aim now is to discuss these two approximate method to deal the problem of motion of electron inside a crystal in very detail. But in this lecture, I will only introduce you to these two approximate methods. That is, we are going to know the key points, the introductory facts regarding this NFE approximation and TB approximation. Okay. But after this introduction, we will learn about these two approximate methods separately in very detail. Okay. So this videos will be very important for you, and particularly for the students preparing for the NET JRF examination or M.Sc or the M.Sc level examination. Okay. So now let us know about some key points of nearly free electron approximation. Actually, when the periodic potential is very weak, and the periodic potential under which our electron is moving, if that periodic potential is very weak, then we can treat it as a perturbation, and we have the nearly free electron approximation. Okay. So nearly free electron approximation will be applied when the periodic potential is very weak, and that potential is just treated like a perturbing potential. And you have studied in your course on quantum mechanics the concept of time independent perturbation and time dependent perturbation. You will see that applying the technique of the perturbed Hamiltonian, we will be able to find the wave function for the electron moving in such a potential. Okay. So when this nearly free electron approximation will be applied, as the name says, nearly free, it means electron is not completely free, but it is almost free, and it will be almost free it will be just like this will behave just like a free electron only when the periodic potential is very weak, not very strong. So in that condition, electron may be treated like just like a free electron, and the potential applied is treated like a perturbing potential. Okay. So what are the key points of this uh, nearly free electron approximation? Let us see. Actually, as you have seen, in discussing the KP model, we have applied Bloch's theorem to find the wave functions of the electron moving under the periodic potential. Actually, in this nearly free electron approximation, we also apply the Bloch's theorem, okay, to find the wave functions of the electron. And you know what this Bloch theorem says? According to this Bloch theorem, the Bloch functions or the wave functions of the electron psi k of r is given like this. This is plane wave e to the power I k dot r times uk of r. Okay. This is just the statement of Bloch's theorem. And here you know this uk of r is a periodic function having the same periodicity as that of the potential. So uk of r has the periodicity of the crystal or it has the periodicity of the potential. Okay. So this idea which was also used in KP model is applied here too. Okay. As you have seen in KP model, the allowed and forbidden energy band actually exist. So actually in this nearly free electron model 2, you will see when we will discuss the theory in very detail, then you will see that energy band gaps arise at the Brillouin zone boundaries. Why these energy band gaps arise? Actually, the cause of arising the energy band gaps at the boundaries of Brillouin zone is the interference of electron wave function with the periodic lattice potential. Okay. Actually, due to this interaction, the energy levels get splitted, get perturbed, and due to the splitting of energy level, different bands are formed. Okay. So when we will discuss the theory in proper manner in our next lecture, then you will see how this energy band is formed due to the splitting of the energy level, and that splitting takes place due to the interference of electron wave function with the periodic lattice potential. Okay. Actually, this nearly free electron model is particularly useful for understanding the formation of energy bands and energy gaps in materials where the electron lattice interaction is weak. As I have told you earlier, that this approximation method will be valid, will be applied only when the perturbing potential or periodic potential is weak. So when electron lattice interaction is weak, then the potential under which our electron will move will be also weak, and in that very condition we can apply this nearly free electron approximation. And this model or this approximation is not valid for all types of materials. If you will try to discuss the physics of semiconductor, physics of insulator by using this nearly free electron approximation, you will be not successful, because this theory is not applicable for all types of materials or all types of solids. But there are a group of materials for which this approximate method can be applied. And a very good example of such materials are actually the simple metals. It means the physics of metals, the conductivity of metals, the thermal properties of metals can be discussed by this nearly free electron approximation. Okay, but this approximation will be not valid, cannot be applied for the semiconductors and the insulators. Okay, so definitely a question has been raised in your mind that if your aim is to discuss the physics of semiconductor and insulator, then what we will do? Actually, for that we have to see about another approximate method, and another approximate method is called tight binding approximation. This is just the reverse condition. As you have seen, in case of nearly free electron approximation, the potential under which the electron moves is very weak. But here the name indicates that it is tight binding approximation. So in this case, actually the periodic potential under which we will consider our electron to be moving will be very strong. And as the potential is very strong, so the electrons are strongly bonded to the parent atom. If there is this is an atom and this is the electron of the atom, this electron is not free to move very away from this atom. The motion of this electron will be localized near the parent atom due to the strong interaction. Okay, atom, or you can say also ion. Okay, so in this case, if or you can say if the periodic potential is very strong, and so that the electrons are bonded to the atoms and their motion is highly localized around the atomic sites, then such an approximation is called tight binding approximation. Okay, tight binding. So this is known as tight binding approximation. Okay, so one thing is clear here, that nearly free electron approximation is applied in case of weak perturbing potential, but tight binding approximation will be applied when the periodic potential is very strong. Okay, so in this case electrons are not free, okay, but they are bonded to the parent atom. Okay, again I am telling you, we will learn about this tight binding approximation in very detail in a quantitative manner by the appropriate calculation of the energy eigenvalue and the eigenfunctions of the electron in our next lecture. Okay, but in present lecture, as I have told you earlier, our aim is only to introduce you about these two approximate methods. Okay, so what are the key points of this tight binding approximation? Let us see one by one. As you have seen just now, that electrons in this case are tightly bound to the individual atoms and only occasionally hop between neighboring atomic sites. So if these are the atoms and you can say this is atom number 1, this is 2, and this is 3, then this 2 and 3 will be called the neighboring atoms of 1. So in case of this, if we consider that the periodic potential is very strong, then this electron will be almost localized near this atom 1. But sometimes it may hop, it may move between 1 and 2. But you can't think that this electron 1 will move to the site of 10th atom. Okay, so the motion of the electron due to the strong potential is localized near the parent atom, or sometimes it hop between the neighboring atomic sites. Okay, actually in this case atomic orbitals are used as the basis of the electron wave functions. Okay? And the electron wave function in the crystal is expressed as a linear combination of the atomic orbitals. So combining the atomic orbital wave function linearly, we get the electronic wave functions. Okay. Then another very important fact regarding this tight binding is the hopping probability, which is also called overlap integral between the adjacent atomic sites, determines the strength of the electron movement between the atoms and atoms, and thus width of the energy bands. Okay, so in terms of, we will learn in our actual lecture on this tight binding approximation, we will obtain an integral which is called overlap integral, and in terms of that overlap integral we will be able to find the width of the energy band. Okay. Now, as the name says, this approximation will be effective for describing the electronic structure of the materials where the atomic orbitals are localized. Okay, as you have seen. And what are those materials? The most important examples for such materials are semiconductors and insulators. So you have seen that by the use of the nearly free electron approximation, we cannot discuss the motion of electron and holes inside a semiconductor and insulator. But for discussing the motion of electron inside a semiconductor or insulator, we can apply this tight binding approximation. Okay, so this approximate method is suitable to discuss the physics of semiconductors and insulators. Okay, and in this case, actually the energy bands are formed due to the overlap of atomic orbitals. When the atomic orbitals get overlapped, then energy band is formed, and these bands can describe the material's electrical conductivity properties. Okay, so now you can think, we have seen that there are two approximate methods, but these are two extreme cases. When the potential is very weak, then you can apply nearly free electron approximation. And if the potential is very strong, then you can apply the tight binding approximation. But think, what will happen when the potential is neither very weak nor very strong, but the value of the potential is intermediate value? It is not very weak, it is not very strong, its value is just an intermediate value. Then what theory will be applied? In that very condition, you can't apply the first method, that is the nearly free electron approximation, and you also cannot apply the tight binding approximation. So actually these two approximate methods are the two extreme conditions. Okay, but if in actual state of affairs the potential under which the electron will move is neither very strong nor very weak, in that condition both of these approximate methods can not be applied. Okay, actually in those conditions when the potential has intermediate values between these two extreme cases, in that intermediate range we must use more complex methods, and for those for that situation the most widely used two methods are orthogonalized plane wave method, which is in brief called OPW method, and the augmented plane wave method, APW method. So these are the methods to discuss the motion of electron when the potential is neither very strong nor very weak. Okay. So this was just a brief introduction regarding the uh, easy limiting cases of the true periodic potential, under which we will discuss in very detail in our forthcoming lectures the nearly free electron approximation and the tight binding approximation. But I hope you have just an idea when why this approximate method is used, why we need it, and how it will be applied, what result we will get. I have not discussed here. I have only given just an information to you. Okay. So this was my aim, was just to introduce these two methods, but the detailed explanation of these two approximate methods we will see in our forthcoming videos. Okay. Thank you very much.